Reinforced concrete structures, analysis of double reinforced concrete section. So in this example, we have a solid rectangular cross section with compressive steel, like what you can see here, two number 7 rebars at the top of the section, and four number 10 like tensile rebars at the bottom of the section. So these are tensile bars, and we also have compression steel at the top. The F prime C 4000 psi specific strength of concrete and strength of steel like P1000 psi. We want to calculate nominal moment, also the design moment for below mentioned section. So the very first step in double reinforced concrete sections is assuming that compressive steel yields and then check it. So this is compressive steel. We just consider that if F prime S, which is like AS prime, and call it AS2, F prime S goes by the strength of steel, and then double check if epsilon prime S, the strain of compressive steel is larger than epsilon of field. That's these two terms are equivalent to each other. And then check it later. If we call AS prime like AS2, that's a two number 7 rebars, as you can see here, and each number 7 has an area of 6 inches squared, so two of them make it 1.2 inches squared. And then, like, if we just assume this is like AS and AS at the top of the bottom of the section is 4 number 10, each number 10 is 1.27 inches squared, and 4 of them make it like AS is equal to 5.08. Then subtract AS, we can call AS1 like the difference between AS minus AS prime, and it just makes 5.08 minus 1.2, it just gives us AS1 is 3.88 inches squared. As soon as we have that, we can go on and calculate the height of witness block. The only difference in double reinforced is AS1 replaced with AS times F5. This time in double reinforced, we just replace it by AS1, which is the subtraction of AS minus AS prime, times F5, which is 3.88 times 50,000 over 4,000, which is 50 over 4, times 85 percentile of 4 times 14, which is the width of our section. It just gives us A is equal height of witness block is 4.07 inches. Then C is A over beta 1 for F prime C equal to 4,000 is 8, and it just gives us the height of neutral axis from the top of the section is equal to 5.9 inches. Epsilon U is equal to 4 here. If we just make a similar triangles, this small triangle versus the here one here, it just gives us the relation of epsilon prime S, which is epsilon U, which is 0.03 times C minus D prime, which is here, C minus D prime is just here, to C is equal to epsilon prime S, if you just take it here, over epsilon U, which is 0.3. We just rearrange the equation, it just gives us epsilon prime S is like coming from this equation. We already know what C is, what D prime is provided from the problem statement, and it just gives us a numeric value of 0.415 for epsilon prime S. If you look at we need to look at the epsilon prime S, which is 15, and our epsilon Y is Fy, the strength of grade 50 steel over ES, which is 50 over 29,000, and it just make it like 17. can easily see compression steel, compressive steel doesn't go yield. Epsilon prime is 0.0015 and it's 15 is smaller than 15 and 17, so it's not going to yield, and we need to either epsilon prime s is not bigger. If it's bigger, then you can replace f prime s. If it's bigger, you can replace it by fy. But if f prime s is less than fy, like which can easily see in our problem statement, epsilon prime s is less than, this is 15, less than 17. So if not, we have two ways. One of them is like trial and error to find the location of a centroid from the top. And the other one is the exact method, which we are going to use. The second one, we are using the exact method, which by solving a second degree equation, it just gives us the height of equivalent height of neutral axis, then equivalent stress, and solving the problem in placing in moment equation. So if we just go by exact method, that's ax squared plus bx squared plus c second degree equation, and it just gives us, and x is just neutral axis like c, and this is x. We don't want to mess up with this c here, that's why we just put it like x squared plus bx plus c, that's a coefficient, and we just measure it from distance of neutral axis from the top of the section to neutral axis. And the parametric value for A is this equation, for B is this equation, and for C is this equation. If we just replace the numeric value in each of these equations, it just gives us A equal to 40,460, B is equal to negative 149,600, and C is a negative 261,000 for this, and if you just replace them in ax squared plus bx plus c is equal to 0, it just gives us two roots of second degree equation. The positive is our answer and negative is can be ignored. So if you just go with this equation, this root is negative and the positive root is x1 is positive 4.99 inches, and that's exactly the location of centroid from the top of the section to the centroid. So as soon as we know what C is, we can replace it in F primeless equation. That's ES from Hooke's law. Sigma is E times epsilon. F prime S is a kind of is a stress. Epsilon is epsilon. And just ES is 229 times 10 to 6 times epsilon C, and we just replace C from our equation, which is 4.99, and D is also provided from problem statement. So if you solve the problem, it just gives us F prime S or F, it just 43,000.4, which is less than 50,000 psi. And if you just make a comparison, that's almost 90% or 87 percentile of Fy. It's not fully yield, but it's close enough to yield. But yet we need to use this equation. Then Mn is a combination of this part plus compressive steel. 5 percentile of F prime C times B times A times D and minus A over 2 plus A prime S times F prime S times D minus D bar. If you replace the numeric value in the equation, 85 percentile 4,000, B 14, A 4.24, D minus, and it just gives us this amount in pound inches. A prime is likewise, A prime is 0.12 times F prime is, which we just calculated, like D minus D prime, and it just gives us 1.12 10 to 6, that's 2.83 10 to 6 pound inches. If we just add them up together and report it divided by 12 inches to feet, and then it just gives us 329.58 kilo feet. So then we just need to go for design moment capacity, which is 3 times mn. And if it's ductile, we are allowed to use 0.9 for flexural member, and mu is equal to 3 times mn, 9 times this amount in kilopound feet. It just gives us mu is design moment is 296 point, mu is 296.63 pound feet. Now we do check the ductility of our behavior. So we want to see if our problem is ductile or not. So the very beginning check of that is just for f prime s, and if f prime s is equal to, again, 4044, and because that's 4000, that's definitely in the first category, and 200 over fy is controlling 200 over 50,000, it just gives us a 0.04, and that's the controlling. And our available row should be density of steel is area of steel over higher section, like by at cross section up to effective depths is 5.08 over 14 times 24. It just gives us this amount of row, and it should be higher than row minimum, which is 4.004, and definitely we have passed the very first requirement, which is row minimum requirement, and the ductility check based off, let's see what is all, it's 50,000 for 50,000, and like for C over D should be equal to 89. As you can see here, that's 3.89. That's C over D. Grade number 15. So that's the number on this table. Steel grade 60, and C over D equal to C over D should be smaller than 0.389 from, for grade number 50 of steel. So C is 4.99, is 24, and that's, it would make it like 0.21, and 21 is definitely less than 389. Ductility check passes because by using phi is equal to 9 is still allowed structure. Thank you. We solve more problem concrete design and analysis of sections. Thank you.